if the universe expansion is still moving at the same rate as it was earlier. Because they figured that it would happen like this, that the universe would expand, and all the matter in gravity in the universe would slow the expansion of the universe and maybe make it start to collapse. So they expect the universe expansion to be slowing down right now. And to check and see if they're right, what they do is they look at redshifts for these far-off galaxies at the edge of the universe. Which means, when I say at the edge of the universe, I mean very far away from us. There is no real edge to the universe. But, because kind of like the balloon, if the universe is expanding, we're all at the edge of the universe. Woo, woo. Hard to wrap your mind around. But for things very, very far away from us, is the expansion accelerating or slowing down or what? And they find out when they look at these things that the expansion is accelerating.
What chapter is this?
This is 17.4. And this is a graph showing these redshifts that they got for these far-off galaxies. So galaxies that are close by have redshifts plotted by the dots here. And galaxies that are far off have redshifts plotted by the dots here. If the dots tend to cluster around this red line, that means the universe, the expansion is decelerating. But if it tends to cluster around this blue line, it means the expansion is accelerating. And it most definitely clusters around the blue line. This is just some of the data they have. They've got a lot more data. And it mimics that blue line perfectly when you total it all up. Which means the expansion of the universe is accelerating. So it started out slow, and now it's speeding up. And that freaks out scientists, because they didn't expect that. Somehow the dark energy that is spreading the universe apart has a greater effect the less dense the universe is. And scientists call this energy vacuum pressure. It's pressure that's pushing in the opposite direction as gravity, pushing the universe apart. They don't know why it happens. Somehow this dark energy is pushing the universe apart. And the dark energy becomes more dominant the bigger the universe gets. And so the expansion of the universe looks like this. Slow at first, and then faster as the universe gets old. And they liken it to a spring, where the spring is pushing out greater and greater, pushing the universe apart. So, this omega naught value that determines the shape of the universe, if you take in normal matter, the amount of omega naught is something like 0.02. If you add dark matter, the omega naught value goes all the way to what, did we say? 0.25. If you add in the amount of dark energy that is out there pushing the universe apart, the omega naught value goes to exactly 1.0. And thus our universe appears flat. the universe is, if the omega naught value is greater than 1.0, we have a closed universe that if you take off in one direction in a spaceship, you'll come back to the same spot. We call that a closed universe, kind of like a closed globe, which is a kind of a neat thought. If you take off in one direction, you come back to the same spot. So in a closed universe, if you flew this way, you'd come back here. In an open universe, if omega naught's less than 1, then that is a saddle-shaped universe, where if you send two beams of light out parallel to one another, they'll actually spread out over time, which is a very strange thought. Just like two marbles sliding on a saddle would separate. Yes?
What unit is this? Like, what unit of measurement is this?
It's not. It doesn't have any units because it's a fraction of the amount of matter that is needed over the amount of matter that is observed.
So this one is add everything up.
If the two numbers are the same, it's 1. If one number is bigger, if the top number is bigger than the bottom number, it's greater than 1. If the top number is smaller than the bottom number, it's less than 1. The bottom number is the mass needed to halt the expansion of the universe to make the universe flat. Okay? So it's just a fraction. It doesn't have any units. So instead of greater than 1 or less than 1, it's exactly 1. And that bothers scientists. Why should it be exactly 1? There's so many values greater than 1. There's so many values less than 1. There are infinite values greater than 1 and less than 1. What makes it exactly 1? Scientists don't understand why that is. Until a new theory was made. Oh, so here's the breakdown of stuff in the universe. 4% of stuff in the universe is normal matter, like we know of, that we understand. 23% of stuff in the universe is dark matter, and 73% of stuff in the universe is dark energy. So we don't understand what 96% of stuff in the universe is.
Wait, what do you call that? The omega thing?
Omega naught is the critical value. What? It has a name. The cosmic density parameter.
That's it, the
Cosmic density parameter. Skipping this. Oh, let me talk about these two guys before I go further into this. These two guys are named Penzias and Wilson. And they made a discovery of the cosmic microwave background radiation. Do you remember I said when the universe was real young and small, it would have been filled with high energy gamma rays? And if that were true, if the universe used to be small and filled only with energy, high energy gamma rays, and it stretched out into the universe we have now, then those gamma rays would be stretched way out, and you would have what? Radio waves. Well, there's a type of radio wave called microwaves. It's the same type of wave that cooks your food in the microwave oven. And these two guys use their telescope. That's a microwave telescope behind them. And it's for looking at these low energy waves coming from cold objects in space. When they got this telescope and they turned it to space and were looking for these cold objects that emit microwaves, they found microwaves everywhere they looked in space. And those microwaves are the high energy gamma waves that have been stretched out over the years by the expanding universe. They discovered them, and it's direct evidence that the Big Bang was real. Because if there was no Big Bang, you wouldn't have these waves. If the universe had always existed, those waves wouldn't be there. They discovered them, and they won the Nobel Prize for it. And that's direct evidence of the Big Bang. Penzias and Wilson are those guys' names. They actually weren't even astronomers. They were checking for microwaves on Earth, I think, coming from earthly objects. And when they turned it to the sky, they saw it coming from everywhere. They were kind of baffled to why that detector was coming up with these waves. So here we go. 1 second after the Big Bang, when the universe was still very small, you had high energy. This is the black body curve, real hot. And over time, as the universe expands, this has gone really low, and there's radio waves emitted that are just floating around in space, that have been floating around for 14 billion years, and they can be detected. Have you ever turned on a TV screen and seen the snow that it makes? We used to have this when I was a kid. If you pulled on an old TV, you see a snowy screen. Do y'all know what I'm talking about? Mm-hmm. Well, the patterns in the snow are changed around by these radio waves at this frequency. So the way the snow dances around on the screen is a detection of the microwave radiation from the Big Bang. We know that now. So the idea we have was at a very early time, the universe was all energy. And as the universe expands, that huge amount of energy gets separated from one another. And one thing that we know that happens is energy will freeze into matter. Did you know that's where mass comes from, energy? The protons, neutrons, and electrons, actually the things that make up protons, neutrons, and electrons, are somehow frozen energy. And you can figure out how much energy it takes to make matter by using Einstein's famous equation. Have you ever heard of it? E equals mc squared?
Sounds familiar.
You heard of that? Let me explain what that formula means. It's a very important formula. You see this paper clip? It has mass. You know how much it weighs? About a gram. 1 gram. Let's plug that into our formula. 1 gram of mass multiplied by the speed of light squared. What's the speed of light? 180,000 meters per second. What do you get if you square the speed of light? Anyone got a calculator? By the way, 1 gram is how many kilograms? Do you know? 0.001 kilograms.
3, 2, 4, 54.
Okay, multiply that when you square that by 0.001.
3, 2, 4, 0, 0, 0, 0, 0.
3 zeros?
It's on competition with
4 zeros?
5 zeros.
5 zeros?
5 zeros.
Okay. So this is, if you take this paperclip and convert it completely to energy, you would have 32,400,000 kilogram meter squared per second squared. You physics people know what unit that is? Have y'all learned that yet?
Meter squared. What is it?
Kilogram meter squared per second
I learned
squared?
that today.
What is it?
I don't remember.
Isn't it a joule?
Yeah, it is.
It's a joule. So this paperclip, if we could convert it to energy, it would produce 32,400,000 joules of energy. That's enough to lift this entire campus and throw it into outer space.
What?
If we could convert that to energy.
How would we do
That's a
such
lot of
thing?
energy. That's how come those nuclear bombs produce so much energy. It takes a tiny amount of matter, and when you get this nuclear reaction that happens in the middle of a nuclear bomb, a little bit of the matter is converted to energy, and you get this huge explosion. You can blow up a whole city with it. That's what happened to Hiroshima and Nagasaki. Just a little bit of matter got converted to energy inside those bombs. And early in the universe, when the universe is expanding, all that energy, as the universe gets bigger, some of the energy freezes into matter and becomes matter. It takes a whole lot of energy just to make a little bit of matter, but it happened because there was a whole lot of energy in the universe. And so all the matter you see was created as the universe expanded, and a lot of that energy froze into matter. We don't know how that happens, how energy freezes into matter. They don't understand the process yet. That's what they're trying to duplicate with these huge colliders. They get protons spinning around these huge colliders real fast, and they ram them into each other and try to create a huge amount of energy, and then see what happens to the energy. Maybe some of it will freeze into matter and form some of these elementary particles that make things. You know, even protons and neutrons are made of smaller things. Did y'all know that?
Yeah.
You know what they're called?
Quarks.
Quarks. And what are the quarks made of? Well, they're trying to figure that out. Strings. That's one theory.
How doesn't he know that?
String theory. Because he's the captain of the science bowl team. That's how he knows it.
I know. I'm not the one asking the stupid questions.
So-
Yeah.
For a while, check this out. This is a graph showing what the universe was like. For a good while, the universe was radiation dominated. That's when the universe was mostly energy, mostly radiation. But a lot of the radiation freezes into matter. And so the radiation goes down as the universe expands. The radiation goes down and the matter goes up. And there's a point where there's more matter in the universe than there is radiation. And so the universe was matter dominated for a good while. And just a few billion years ago, the radiation became dark energy dominated. Now there's more dark energy than there is matter or radiation. And that's why these numbers are so much smaller. If you total the normal matter and the dark matter, you're less than all the dark energy. You're only 25%. The dark energy makes the other 75% of what's out there. We are a dark energy dominated universe. The dark energy level has stayed constant. Since the beginning of the universe, there's the same amount of dark energy now as there was at the beginning of the universe. But the density of radiation and matter has gotten a lot less as the universe has expanded. This is great Science Bowl stuff. You'll hear some of this in Science Bowl, you guys that are in it. We're in a dark energy dominated state, and that will continue forever as long as the universe is expanding. And we think the universe will expand forever because it's accelerating its expansion. If it were slowing down, we might have reason to believe it's going to collapse. But it's accelerating. And so we have reason to believe that the universe will end up this cold place, this dark place, after it becomes so big that all the galaxies are so spread out. Eventually all the stars will burn up all their fuel. And there will be a point trillions and trillions of years from now where the last star goes out and there's no more light in the universe.
Talk about depressing.
And eventually even all the stars, even the black holes and things that are there, all the matter will eventually degrade and erode. There's something called proton decay, where individual pieces of matter just turn to energy. And we'll be left with trillions and trillions and trillions of years in the future. There'll be nothing in the universe except real spread out electromagnetic waves that are approaching being infinitely weak. The universe will be completely cold and dark. Fractions of a hair above absolute zero. Fed only the temperature of these ever-expanding waves.
So do you think life by that time would be able to control that type of stuff?
I don't know.
How do they know there's not another section?
It's actually a physical certainty that it will go there, and even life would have to do that too. That there's not enough energy in the universe to keep it from happening. Who knows if that's really true? Exactly, yeah, it's one of the laws of physics. Who knows if that's exactly true? But that's the way it looks right now, from what we know. That's how the universe is.
How do they know that there's not another section like fast dark energy?
This is all we know for now. Maybe there will be. But see the density of radiation and the density of matter will continually go down as the universe gets bigger, because density decreases as you increase volume. So these are going to continue to go down, and this, as far as we know, will stay the same. So we don't see anything more than a dark energy dominated future, unless there's something else that we don't know about that will happen.
The dark energy collapse into dark matter.
Perhaps maybe when it gets so diffused, something happens with the dark energy and it gets converted to matter or energy, and the whole thing reverses or something. We don't know any of that stuff. This is stuff they might figure out in the future. So, as far as we know now, that's what's going to happen. I read a cool article in one of the magazines that the title of the article is "The End of Everything," and it just goes into describing all these changes that will happen, and eventually you're left with nothing. And it's trillions of years into the future. Because for now, these stars explode and all the junk goes everywhere, and some of it comes back to form another star. And then you go through the life of a star, which is hundreds of billions of years, and then it explodes again, and then the stuff comes back together. But eventually, every time it does that, some of the matter is converted to energy, you see. So eventually, all the matter will get converted to energy. You won't have any matter left to do that. But it takes a long time. It's unbelievable. I just can't fathom it. So you read through 17:6, okay? And we pick up the next time. You can stop filming. Thank you for doing that.